In this video, we'll discuss the variance of a random variable, and we'll discuss the definition of the variance from a numerical perspective, in the context of a very simple example. And I hope that this will clarify the definition of the variance. The variance of a random variable x is defined as the expected value of a transformation of x, and the transformation takes the following form. We take x, then we subtract its expectation, which is just a number, so we subtract a certain number, then we square the result, and this then here, the blue part defines a new random variable over which we can take an expectation. And one way to interpret the variance is to think of this as the deviation of x from its average, and then taking the expectation here just means computing the average squared distance. Let's look at this using a numerical example. For our random experiment, we need possible outcomes. Let's call those omega 1, omega 2, omega 3. Each of those outcomes has a certain probability. Let's say the first outcome has probability 1/6. The second outcome has probability 3/6, and the third outcome probability 2/6. Now let's define a random variable x. X takes a different value for each of the possible outcomes. Let's say it takes the value -2 here, the value 0 here, and 4 for the last outcome. To compute the variance of x, we definitely need the expectation of x. So let's compute that first. Let's remind ourselves how the expectation is defined. The expectation of the random variable x is computed by summing over all possible outcomes omega. So every row here gives information about an outcome. So what we're doing here is we're iterating over the rows and summing numbers. Specifically, what we're doing is we take the value of x for the outcome and multiply it by the probability of the outcome. Let's compute the sum for our numerical example. So we're starting with the first row, the first outcome. We're taking the value of x under this outcome. The value is -2. We're multiplying the corresponding probability, which you find in the same row here. It's 1/6. Then we move on to the next omega, which would be then, which we can find in this row. We take the value of x, which is 0, right? 0 times, we multiply the corresponding probability, 3/6, and move on to the next outcome, get a value of 4 with a probability of 2/6. And since here we have the summation operator, all of these are connected. All of these terms are connected by a summation sign. So we're summing up all of these terms. All right, let's compute the sum. it's fairly easy to compute despite here being fractions, because all the fractions share a common denominator. So we can just compute them fairly simply like this, right? The common denominator goes here, and now we do minus 2 times 1, that's a minus 2, plus 0 times 3, that's a 0, plus 4 times 2, that's an 8. So minus 2 plus 8, that is a 6. 6 over 6 is 1. So now we've computed the expectation to be 1. Let's move on to the variance. The variance of x is the expectation of the random variable x minus expected value of x, and we square all of this. So with this coloring scheme, it may look less, it hopefully looks less intimidating than it would otherwise, because what we realize now is we just have to understand how this random variable is defined, and then we can just then we can apply the same recipe that we used here, except for the blue x, we will have a green random variable that takes a slightly more complicated form. We determine the random of the value of the random variable for every outcome. So for every row, right, we have a value for x. These values were already given, and now we just add the value for x minus ex squared. X minus expectation x squared. And I'll do this in 2 steps, so hopefully that will make it a little easier. So I compute x minus expectation x first. So for the first outcome, so we're in this row, x is minus 2 minus the expectation of 1, minus 2 minus 1, that's a minus 3. The next one will be 0 minus 1, which will be minus 1. 4 minus 1 will be a positive 3. And now to get the values of x minus expectation x squared, I just have to square this column here, and I get 9, 1, 9. And now I can apply the same recipe here, right? All I have to do is compute an expectation of a random variable, which is exactly what we did here. So obviously the same recipe applies, but instead of taking the x values, we're taking the corresponding, instead of taking the blue x values, I should say, we're taking the green values of x minus expectation x squared. Okay, otherwise it's exactly the same. This is equal to, we start with the first outcome where we take the x for this outcome, which is 9. We multiply by the probability 1 over 6. Then we add the same thing for this second outcome. We're moving down from this row to working with this row. So we have 1 times 3 over 6. Then we are adding the last outcome, which again is a 9 with probability. This time it's 2 over 6. Okay. Adding this up is fairly easy because they share the common denominator 6. And in the numerator, we're adding 9 plus 3 plus 18. So this will be 12 plus 18, 30 over 6, which is 5. So now we found the value 5 for the variance. This value 5 that we found here is the numerical value for this example of the variance of x, and x is the random variable, and you could consider x a GGP, or x could describe a population, and we can compute its variance if we have very detailed knowledge about the underlying distribution of x. If you want to emphasize that the variance of x is a feature of the population, you could call the variance of x that we computed here the population variance. And why would you want to emphasize that? Well, there's a different variance of x, the sample variance, which you can compute if you have a sample of x, so multiple random draws from x. So let's think a little bit more about the difference between the population variance of x and the sample variance of x. And as always, I use hats to indicate that something is computed on a random sample rather than using the true underlying population distribution. To compute a sample variance, we of course need to have a sample. So for a random sample, we usually label the observations by a running indicator that we often call I, and we'll just call them 1, 2, 3, 4, and let's say that this is how many observations are in our sample. So 4 would be what we call n, the sample size. For every observation, we draw a value of x. We call this xi, so it will be x1 for the first observation, x2 for the second observation, and so on and so forth. Now, how do we draw x1, the first observation? Well, we draw it from our population, so we just have to make sure that we draw a -2 with probability 1/6, a 0 with probability 3/6 or 1/2, and so on, right? One way kind of that we could do that is by saying let's roll a dice, and if we roll a 1, we'll say that we have drawn the first outcome, so we observe a value of -2 for x. If we roll a 2, a 3, or a 4, we say that we draw the outcome, the second outcome. If we roll a 5 or a 6, we say that we draw the third outcome and hence observe a value of 4, right? So we could implement this sampling process by rolling a dice. So let's suppose we do that. We roll the dice and we see we roll a 1. That means we draw the first outcome and hence observe a value of -2 for the random variable. So this will be our first observation, x1. We put the -2 here. And then we repeat the process 3 more times, and let's suppose that we get another -2, a 0, and a 4. For the population, we defined the notion of the expectation, which can be interpreted as an average, and we can do something similar for the sample. And because it's the sample, I'll call this expectation hat, basically. For the hat reminds us that this is computed on the sample, not using the underlying population distribution of the random variable x. And what I want to do now is just replicate this pattern that we see here. So I will not be having any omegas, so instead I'll be summing over the different i's. So I take I from the first observation to the nth observation, which is 4 in this example, but I'll just write n is 4. Then I'll take x, but this time not x of w, but x observed at observation I, x observed at observation I, and now I realize I don't have a probability measure. So right in this table there's no p. So I'll invent a p, and what we'll use is empirical measure. And empirical measure just gives the same weight to each observation. We have 4 observations, so every observation gets weight 1 over 4, 1 over 4, 1 over 4, 1 over 4. Okay? So let me add this here as well. Empirical measure of observation I. And since it's the same for every observation, I may as well just write 1 over 4, or, right, if we are more general, 1 over n for the empirical measure of observation I. This average that we defined here is called the sample average. Let's compute the sample average for this example. We iterate over all the i's. We start with the first I, or the first row. This is very similar to our previous calculation. So for the first observation, we observe a -2, and we multiply the empirical measure for this observation, which is 1 over 4. Now we move on to I equal 2, and it's -2 again, times 1 over 4, and so on. Now we could just compute the numerical value of this sum, but let's not do that. Instead, let's realize that we have the 1 over 4 here for every term in the sum, so we may as well write 1 over 4, and then in parentheses -2 plus 0 plus 4. What we have here is the sum of all the x's, so it's just the sum over this whole column. We can write this as the sum over all I. We're summing the xi's. And then here, what we're doing is we're dividing by the total number of observations in our sample, 1 over n. We could have used this formula from the get-go, and you can see this by the fact that we can just rearrange the formula up here, just moving the 1 over n to the front, and now here you have the standard formula for the sample average. This is the formula you may be familiar with from introductory statistics courses. This will be like the standard formula that you find on Wikipedia. It's mathematically more natural, but it obfuscates the similarity of the sample average and the expectation. You remember for the expectation we had the weight here, and now we just move the weight from here to up here in front of the sum. What is left to do for us is to compute the numerical value for the sample average in this example. So we have to compute the sum, which corresponds to summing this column. So we have -2, the sum here would be 0. So we have 0, we divide it by a sample size 4, so that's a 0. The sample average for this example is 0. In a similar way, we can define a sample variance. The population variance was defined as the expected value of the random variable x minus expected value of x squared. Now, using the principle of the method of moments, we can just replace these population expectations by sample averages, what we do is that we put a hat on here, we put a hat on here. This is a reasonable way to define a sample variance. Let's make this official by calling this the variance of X. But it's not the population variance, it's the sample variance, so we put a hat on it. Now remember that in this example, this was 0. This will make it a little easier for us to compute the sample variance, because we can just think about the sample average of X squared. We know how to compute a sample average, right? We add everything and then we divide by the number of observations. Before we were adding all the x's, now we want to add all the x squares. So what we wanted to do here is add a column with all the x squares. So we square minus 2, that will be a 4. 4 again, 0. Now we square 4, that will be a 16. We sum over this column, 4, 4, 16, so 24. 24 divided by n, which is 4 here, so that would be 6. The sample variance has the value 6. The purpose of this video was to give you simple numerical examples to illustrate the computation of the variance and the sample variance. We have done that now. So let me just conclude with one last remark. If you don't like the Ehat notation, you can just write the sample variance that I defined here as 1 over n, right? Because it is a sample average. Sum over all the observations, xi minus the sample average of x squared, right? This is completely equivalent. This is just expanding what is hiding behind this Ehat notation. Now when you write it like this, it may look similar to a formula that you've seen before, a formula for the sample variance that you've seen before, but maybe previously in the formula there wasn't a 1 over n here, and instead there was an n minus 1. This is another way to define a sample variance. There's nothing wrong with it. It is no longer a method of moments estimator, because you have weights 1 over n minus 1 and not instead of 1 over n. There are valid reasons to use this definition and not my definition. In practice, it doesn't really make a difference, because whether you divide by 1 over n or 1 over n minus 1 will not make much of a difference if n is large. So basically we're talking about changing the definition of the variance by the factor n over n minus 1, which if n is reasonably large, if it's like 50, 60, 100, is basically 1. So for all practical purposes, it doesn't make much of a difference, and I find this formula much more difficult to motivate than my formula, and also more difficult to remember. So we just stick with 1 over n for this course. So that's it. That's all I had to say. Thanks.